Okay, I'm going to start because we have a lot to cover this afternoon. So let's see. Good. So welcome to our third MATLAB for image processing session. And happy Women's Day. And thanks for all the female scientists in the group that are joining us today. It means a lot. Today, we are going to cover some exciting stuff, but before that, I'm going to tell you what we did last session. So briefly, we covered some of the points, some of the important points of the first session. And we learned how to import data, how to do indexing and logical indexing, how to create plots. And we solved numerous problems, and we had exercises for this session, which I hope you have done and completed them. And today we are going to have an overview of the important things in session 2. And we are going to do some basic programming. Not that we haven't been doing programming so far, but just some basic stuff, including conditions and loops, as in decisions and loops, however you want to call it. And as usual, we're going to solve a number of MATLAB problems, and I'm going to start our image processing if time allows me to. But before we move on, I'm going to ask you to complete this brief, less than 1 minute survey for me. You must have it in chat now. By the way, if you follow the usual link to the material, all this, the slides are online for session 3, and we have a few more things. So if you want to have the slides in front of you, the slides are already there in PDF format. So please take less than a minute to complete the survey. I haven't done any evaluation for the course so far. So this is just to give me a rough idea of how you feel about the session. I will be quiet for a minute so you can complete the session, the survey. Good. So I think you have completed all the 5 or 6 questions so far. If you have any further comments that doesn't fit in the tiny box, please just email me, drop me an email, and let me know how you feel about the sessions, what you want to see in the sessions if they are not already there. So I'm going to go directly to the exercises from our previous session. So we were supposed to complete the project section, section 10 of the MATLAB on-ramp. And we had a few questions, a few like very tiny exercises as well. So I'm going to first begin with MATLAB on-ramp, if you don't mind. So if you want to navigate to section 10 on on-ramp, I will wait a bit for you to just go there. So the address is matlabacademy@.mathworks.com, and then you should just navigate to on-ramp, and then it's section 10.1 that I'm looking at. So it has a pop-up window coming up first that talks about what you're going to see in this exercise first. and then you can see the questions, and we go through them in a bit. So yeah. So the first question, the first task is load the data. Oh, okay. Yes, I'm still here. Load the data into your workspace and then enter usage to see the usage matrix. So simply loading the data, it is called electricity.mat. You can use your tab key on your keyboard as usual to complete the command. I'm going to load it. I'm going to use semicolon so I don't see the data, but I'm going to enter the command usage to see the output for usage, what is inside the usage matrix. So if I press submit, it's going to run these two commands, and this is the output that I'm going to see. I'm going to click on workspace so you can see what we have. So loading electricity.mat, we have two matrices loaded. So they are both double and of size 23 rows by 3 columns. And inside them, since they are double, we expect to see a lot of numbers. So now if you enter usage, you see that usage is basically a matrix of numbers. So you check that everything is correct. If you needed a hint or you want to look at the solution, but we already have done it, you can click on these, or if you want to reset, you can click on reset and start all over again. So next task, it is telling me that there is a NaN, which stands for not a number, in the usage matrix. And we want to replace it with a value of 2.74. So imagine that I don't know what I have in the matrix. Sorry, I did that. Okay. Oh, the MATLAB Academy. I think Nicholas means this website. So this is the MATLAB Academy website, Nicholas. Sorry, I missed your question. So imagine that we don't know where this NaN cell is. So I can see it here, but imagine I didn't know where it is. So if I click on it, I can see that it is on row 2 and column 3. But imagine that I didn't know. How do I do it? So the first thing, since I can see it, is that I say, oh, it is in row 2 and column 3, and I want the value to be 274. So that's one way of doing it. Another way of doing it, as I say, imagine we don't know where this one NaN value is. So you can use something like this. So you can say usage is NaN usage, and then put 2.74. So how does it work? So it is going to look for any NaN value inside the usage matrix. So this is from the previous session. We talked about isNaN. isNaN is a function, built-in function, that is basically going to help us find any values that are NaN inside a matrix or any input that you give it. So our input for the function isNaN is usage. And I'm saying any NaN value that you find using the isNaN function inside the matrix usage, equalize it to 2.74. So I'm going to comment this, but basically any of these that you submit is correct. So yes, the NaN value was replaced correctly. And are there any other elements that are changed? No, nothing else is changed. So if you now go to your workspace and look at usage, just double clicking on it, you can see that row 2 and column 3 is now replaced by 2.74, whereas previously it was a NaN value, as you can see here. This is showing us the first task output. So next, we want to create a variable called res for residential data that contains the first column of usage. So we did this several times last session. So we want to index into usage and we want all the rows of the first column. So all the rows of the first column. This is how you do it. So you put colon, double colon to specify that you want all the rows, and then first column you specify 1 in the space that is provided for column. And you assign that to a variable called res. So that is correct. We did that. Next, the commercial data and the industrial data are stored in the second and third columns, respectively. So we want to create 2 new variables called com for commercial and ind for industrial. And what they have, what they are going to contain is the second and the third column of usage. So it is very similar to the previous task. All the rows in the second column are commercial data, and all the rows in the third column are the industrial data. So I'm going to submit that, and yes, both variables exist now, and the values assigned to them are correct. If you have any questions, please either put your mic on or just type it in and I will stop and explain things. So the usage data was collected annually between the years 1991 and 2013. The YRS variable you create will help you to plot the data over a meaningful range. So we want to create a vector named YRS that represents the years starting at 1991 and ending with 2013. So we want to have a new variable that starts with 1991 and ends with 2013. So simply, you want a row vector, a vector matrix, a vector array that contains numbers between 1991 and 2013. We did a similar thing for one of the exercises in the previous session. So that started from 1900 to the current year. So we submit that, everything is fine. Okay, now we want to create a plot with all the 3 columns. So use years as the X data, use this order and these plot specifications. Res has to be blue and com has to be black with dotted line. Industrial has to be magenta with dashed dot line. So how do we do that? So we discussed plots. So I can plot these individually, but it is telling me to plot all of these in the same plot. So we use the hold function, built-in function, to hold the figure that is created and to plot multiple things on top of each other. So how does it work? We know that years has to be our X data, and then initially res with blue dashed line, and then we need to plot years as X and commercial data black dotted line, and the last one is years as X and industrial data magenta and dash dot. So if we submit that, we're going to, it's going to take a while to plot. Yeah, okay. We're going to see this figure. So on the x-axis, we see the years. So in order to have the final number, we know that the data was up to 2013, but it is showing 2015. And it starts from 1990 something, one, I think. And we have the y-axis for 3 different values that we had, 3 different sets of data that we had. And the final task is add the title. So we use the function title. So it is supposed to be July electricity usage. And then create a legend with the values res, commercial, and industrial legend. And you simply just put them in order of plotting, as we discussed last session. And industrial. So you can submit, and you have the final output. So this is the title of your figure, and this is the legend. As you can see, sometimes it's not in the right place. You can simply drag the legend around. So it didn't work for me, or did it work? Sometimes it takes a while because this is the online platform. But yeah, if you try it on your MATLAB, we will do this later, and you can see that you can drag the box around. You can even modify it to not have a box, this black box around it, and different things. So you can modify your figures, basically. So that was it for the first one. Let's move to the second one. I'm going to, of course, you can see the answers online as well, but I'm going to upload the answers as a live script to the folder as well for session 3. So this is the information. This is audio frequency data that we are going to see. So the first thing is to load the data. So I will just quickly go through this because I'm sure you can do this, or you have already done it. So another function that is very useful is the function called numL, which stands for the number of elements in any array. So we want to create a variable named n, and we want that to contain the number of elements in y. So we use the function, built-in function numL for that. So I just put semicolons. And then use n to create an evenly spaced vector t that starts at 0, ends at n minus 1, and has elements that are spaced by 1. So this is simply what we did in the last example, and also in the previous sessions exercise. So you're just creating a vector that has numbers from a certain number, which is 0 here, up to n numbers, n minus 1, whatever that is, that n is. So if we don't know what n is, I would just submit that. And then you can have a look. Okay, n is 12,288. And so t starts from 0 up to that number. And we loaded the data. So the data includes fs and y, because these two are the ones that we created. So moving on to the next task. So divide t by fs, assign the output to the same variable t, then plot y against t. So we want to assign the output of the division t by fs to the variable t, and then we want to plot y against t. When they say y against t, t is your x, y is your y. So that's how you do it. And this is the output. So this is basically the plot of y versus against t. So t is time here, as you can see, this is your t, and these are the values of y. And you can literally zoom into this and do different things on it. So if I want to zoom in, you can literally choose this option and zoom in, or zoom out step by step. So you can just look at how the image is as well. So it's just like a time series output. Then it is introducing fast Fourier transform here. So FFT, if you have done some electrical engineering, you might be already familiar with this, or if you have done like some applied math, this is something that is used a lot for time series data. So the task is telling us to create YFFT, which contains the absolute value of the discrete Fourier transform of what. So we have two functions here. So first we have the absolute value, and then we want to take the FFT of y. So we don't want the negative values of FFT, we just want the absolute value. So it is going to invert all the negatives to the positive. And that's going to be assigned to YFFT. So everything is fine. Again, if you have any questions, please stop me. Then we want to create, again, an evenly spaced vector f from 0 to n-1, and which is spaced evenly by 1. So that's simply like the value of t. So it is simply the same. You submit that. And task 5 is telling us to multiply f with fs over n and assign the output to the same variable called f. So we have f, and we just simply want to multiply f by fs divided by n. So all these variables, f, fs, and n, are already in our workspace. We're just using those to do some more calculations. So we are modifying f now. Then it is telling us to plot YFFT against f. So plot f and YFFT using the x limits of 0 and 1000. Okay, xlim is something we have not used before, so the point of this exercise was to make you familiar with this. So xlim, I will show you what it does on the figure. So basically xlim is going to limit the outputs of our x-axis, and you have a similar function called ylim, which can limit the outputs of y that are shown in the figure. So we simply are plotting YFFT against f, which is frequency here. And these are the FFT values of this signal, basically. And we are limiting the output from 0 to 1000. So this was the final task, I think. Yeah, and it tells you that you can simply click on different parts of your image and see the values. So if I click on these, I can see the values of each of these peaks. So these peaks are very important. Sometimes if you have sensor data, for example, you might want to focus on these peaks. So these can be your useful features. So that was our exercise from MATLAB on-ramp. So let's move to the exercise from what we had in the second session. I'm going to increase the size of this. So this is basically the exercise. Any questions on the on-ramp questions, on-ramp exercises, on-ramp project? I will open my Teams to see. No. Good. I will move on because we have a lot to cover. So the first exercise is telling us to import the hospital data to your workspace. So hospital data, we did that last session, is one of the built-in data sets, sample data sets that MATLAB has. So if I run this, you can see that this is the hospital data. What type of data is hospital? The answer is table. We discussed this briefly. I mentioned it even in the session. So table is a very useful type of data because it can contain different types of information in it. It can be numerical, text, strings. These are categorical, male and female. It can contain anything, basically, table. And it's very easy to use. It's easy to index into it. And if you can work with table, it is highly recommended. So the answer to this is that it is table. Then we want to calculate the mean and standard deviation of age in the data. Some of it is cut, okay, and save them in different variables. I will just move this here. Okay, so this is very good practice. I would type and I will explain to you what I mean by that. So we are trying to index into hospital. Indexing into a table is dot. Pay attention to the way I'm naming these. So I'm using age as the first phrase of my variable name. It is useful to keep an eye on these because sometimes you have so many variables in your workspace and you can't find necessarily what you have named a specific variable in your list of commands in your script. It is useful to give it some name that you can later on find it. So if you have a list of mean variables and the word mean is important for you, put the mean in the beginning and just put mean underscore age or mean whatever. But if the value of all the values that are age related are important for you, just put the age first because then it lists all of them together and you can find it easily on the list of your variables in the workspace. It's just for you, it doesn't really make any difference what you call them. And this is the standard deviation of age. So if I run these, you can simply choose them, right click, and the first option is evaluate selection in the command window. What it does is that it basically pastes them here, copies and pastes them here, and then presses enter. You can do that as well. It just runs them basically. So as you can see, the mean age is 38.2 and the standard deviation is 7.22 almost, if we round it up. So here we wanted to just play around and try median. So I'm just going to create median of age. Again, built-in function. You don't need to create something that exists before. Just use it. So this is the median. Then maximum value, age max. Again, these are stuff that we did previously. So max and min were the functions that we used in the first session, I think. And hospital.age. So you can literally just do different things with this data. So it has some other variables as well. So for example, another good thing to do, we have weight here. So let's see what the mean weight is. And then like the standard deviation of hospital dot weight. So this is another thing that you can just do. So we have now the mean of the weight of the participants and the standard deviation. So another thing, for example, for me, these are all in pound, I think. So if you want to convert it to kilogram, 1 pound is equal to 0.45. So if you wanted weight mean in kilogram, you can just literally do different things with this data, just practice. And all you need to do is to multiply it by 0.45. And that converts all these values. Even you can just do the weight column in the hospital and just have the mean value of that later on, or in kilogram if you are interested. So that's the mean weight. Then we had image data import and plot. So good practice, always start fresh. So this is a new exercise. It has nothing to do with the previous part. You can clear all the workspace variables and you can clear your command window and you can close all your images. We don't have any images open, but just in case. So I'm going to start fresh. Good. Load the image called peppers. So we talked about this before, that if you want to load an image, you can use the function called imread, image read, and that's the way you do it. So peppers.png is again an example image that exists in MATLAB when you install it. So you don't need to really find it or anything. You just do that, and this is the image. So as you can see, it has a value of it's all numbers inside, and we will talk about it when we get to the image processing part. But let's show it and see how it looks like. So I stored the output. I saved it in a variable called pic. So if I want to show it, I use the function imshow. And a new window opens with a figure. And this is how it looks like. It's just different types of peppers. And it has garlic in as well. But yeah, it's basically peppers. So I'm going to close this. So the point of this exercise was that you can't plot an image. You can't use plot, or even for this value that is this variable that is a 3-dimensional, you can't use plot3 either. So if you want to see the image, you use the function imshow. So this exercise is the one we did previously. So I'm going to go through this again because we had some questions on the age part of it. So I'm going to start fresh because again, we don't have anything to do with the previous part. We can clear and close the image and everything. So we had a variable called this year, which is this year. Good. Now we need to create an array from 1900 to this year. So we call it years, and it is, as we did it before, a vector of numbers just from 1900 to this year, and that's that. So create a variable called b, which is equal to the year that you were born. So this is my year of birth. Create a logical index into the array years for the years since you were born. So this stands for basically all the years that I've been living. So it is basically more or equal to B, which was 1985. So B was 1985, and I'm saying that I want to index into all the years that are more than that and equal to that. So then we need to create an array the same size as years, containing your age in each year and zeros before you were born. So as I mentioned, it is easier if you create the 0 one. So I want a zero function, a zero variable of the size years. So it has to have the same size as years. So that's the way we do it. We talked about it last session. But how do we do the age part? Now we want to have it in a way that it contains my age in every single year. So the way we do it, we say, for those parts that I was alive, now do this. We index into the function years, and I know that my age for each of those years is the value of years minus my birth year. So that's the way we calculate this. So I'm simply saying, for example, if it is year 2000, what was my age? So you simply index into years using this, because this specifies which cell in the variable years we wanted to look at. And then we just take my age, my birth year out of it to find out my age. So that's how we calculate the age. Peter did it differently, but it's simpler this way. I think you can do it however you want. So then we want to plot age against the years in blue circles. We did that. And then you want to create an index for years that you were an undergraduate and overplot your age in red triangles for those years, or red circles, however you want to do it. So my undergraduate years, I actually had to go and find out because I didn't remember last session. So it is this until years less than or equal 2008. So these are my undergraduate years. We select them. And then we want to hold the plot. So imagine if I had evaluated all of these lines, I already had a plot. So we want to hold that plot and then plot years of my undergraduate against my age. So we simply index into those values. And then you need to say hold off, as you remember. So if I run all of these, basically we will have something like the plot that Nicholas sent us last week, or the plot that we saw all of us. So basically these are my undergraduate years, and these are the years that I was alive up to now. So I'm going to, yeah, you can close it, or if you want to see how the function close all works. So CLC close all and clear for clearing workspace. So imagine that I still have this open. If I now run this line, it's going to close the image, clear my workspace, and clear my command window. So that's what it does simply. So if you have a fresh script, it's nice to do that. So this is one of the examples of the MATLAB website itself. So we just want to plot some stuff. So we need to create a variable called t using line space from 0 to 10. And we want it to have 101 values. So this is the way you do it. So this is a very useful, again, built-in function, line space. So then we want to create y, which is sine of 2 times pi times t, and z, which is the cosine of 2 times pi times t. And then you want to plot these against t. So plotting that, it needs to be red, and it needs to have a line width of 1.5. So I'm doing it quickly if I run this, we will see the output. And this is the plot so far. So now we want to plot T against Z as blue as a blue line with star marker. So plot T and Z and blue line and stars. So if I plot that, it's going to replace the previous plot with this. So this is now again figure 1, but it is the cosine version of it. So we want to do this using hold. So plot T and Y and R with the line, line width of 1.5 and plot T and Z with blue line stars. And then you just say hold off. And if I run this part, I'm going to see this. So this is now plotting them in the same figure. And then we wanted to use subplot to do that. So subplot, simply we know that we have 2 rows, 1 column is enough for them because we just have 2 figures. So I'm going to just copy and paste them to this part because the commands are the same. We just want to plot them in a new figure. So this is now how it should look like. So this is the sine part, the sinusoid part, and this is the cosine part. Any questions on these? You can even put it in the chat or just put your microphone on and ask me any questions. No? Okay, so I will just continue. I will close this and let's go back to our slides. So as a reminder, we talked about scripts previously. So any set of MATLAB commands that are saved into a text file with a .m as the extension is called a script. So scripts are useful because you can just enter as many commands as you want and keep it for later use, so you don't lose what you've been doing. You don't need to always go to your history to do this. So I'm going to put this on so I can see if there are any questions as well. Good. So yeah, the whole script can be run simply by entering the file name without .m after you have saved it, of course, on the command line or clicking on run from the menu bar. We will do this later. I will show you how. So it is going to execute in the interactive workspace exactly as if you entered each line by line. So MATLAB is going to go line by line in your script and just execute the commands that you have entered. And of course, MATLAB can access all the variables that you have used previously or you have created previously in your workspace. So it is useful to have those variables predefined if you have a specific script that you want to use. So any variable created by the script remains in the workspace when it has finished running. So if it is creating new variables as it is going ahead in the lines, it just keeps those variables in your workspace. What is new, and you haven't had this before, is the if statements. So The generic form of if statements is that you have a condition and you want a certain command to execute if that condition is met, basically. So the generic form is if condition, then your statements go here, and there is an end to finish what you have started. So as an example, I want to display A is negative, just display it. So we use this function to display a string in the command window. I want to display this if A is less than 0. So if A is negative, I want to display A is negative as a text in the command window. So that's a very simple example. So the condition is a logical statement. So it is either true or false. So if it's true, it's a 1. And if it's false, it's a 0. It's digital, 0 and 1. So, and your statements can be any valid MATLAB command, any valid MATLAB statement. So you can display something or just run new commands, do calculations, whatever you want. But it is only going to happen if that condition is met. If you had a condition that is either, for example, true, or you don't want it to be true, and you want different commands to run based on these, you can use if and else. So the generic form is if the condition is true, you have your statements. Else, as in if the condition is not true, you have different statements. For example, if A is negative, you just show A is negative. And if A is not negative, then you just show A is not negative, so it's either positive or 0. So you basically can differentiate these and show it. You can have more than one condition for if, so that's when you use else if. So for example, this is missing something. So the generic form is if condition, and then you have your statements. Else if, again, here it should be condition. Sorry, it is missing. So else if you have another condition, and then there are more statements. And if none of those two conditions are true, then MATLAB just executes these statements. So as an example, so this is the true, this is the correct format. This is missing one word condition here. So as an example, if A is negative, it displays A is negative. But if the variable A is positive, it is going to show this statement. So it is A is positive. If none of these is true, it is going to show A is neither. So it's neither negative or positive. So that's for if. Next, basically form is the for statement. So for is very useful because you want to create a loop in MATLAB to do something, some tasks repeatedly, to do some commands repeatedly. That's when you use for. So the generic form is that you initialize a variable by the first beginning number, and then you have steps, and then you go to the last number. You will see these in the examples. Don't worry if you don't know what's happening here. And then you have your statements. For example, you have 4, then it starts from 1 to 10. So it starts from n is equal to 1 for the first loop. Then it executes this. So x1 is 1 to the power of 2. And then it goes to the beginning. N becomes 2, next value. Then you have x2 is 2 to the power of 2, 4. Then it goes to the beginning, n is 3 this time, and it continues the loop until n is 10. And then it goes x10, 10 to the power of 2. And then that's the end of the loop, so it goes to the rest of your script. So loops are quite inefficient in MATLAB. It is better if you can replace them. So for example, for this example, if you want to replace it, it's better if you use this. It is faster, it's more efficient. There's no difference, the answer is the same, but it is faster if you do this. And if you can vectorize your code instead of using a loop, just do it, because this is basically called vectorized. If you can't do it, do it. If you are if you find it more convenient to use loops, then use loops. Another form of loop is while. So we have while loops. The generic form is while a condition is true, run these statements, and if it's not true, then finish it. So always we initialize a control variable for while before we start looping. So our control variable here is n, which is equal to 1. So our condition is as long as or while n is less than or equal to 10, run these commands. So what are the commands? So that's the same as the previous example. It's going to just put n to the power of 2, whatever the variable is. And then it's going to increment the value of n by 1. So as you can see, by the end of first loop, n has become 2 because n was 1 to begin with. The first loop was executed, then now n is 2. So n goes up. 2 is less than 10. Yes, it is. Then we continue. Then it becomes 3. 3 is less than 10. Yes, it is. Until you get to 11. And 11 is not less than or equal to 10. So that's when you go to end and you carry on with the rest of your script. So the statements within the loop are executed repeatedly as long as the condition is true. We talked about it. And the example does exactly what we saw in the for loop. And again, both for loops and while loops are inefficient. So if you can avoid them, just avoid them. And if the condition is false when first tested, the statement in while loop will never be executed. So if n here, this initial n was 11, then of course this would never happen. It just skips this part. While loops are often used where we don't know in advance how many iterations of the loops we are going to have for a specific task. So, for example, here we have a condition that is done is false. We have initialized the value, and we are counting. So count is 0. So as long as done is not true, which here it is not true, this is the sign of not. So as long as done is not true, it is going to run this part. So it is going to add 1 to count. So count was 0, now count has become 1. And it's going to have these statements executed. So these are predefined. This is just an example, obviously. We have had B1 and B2 in the workspace, and we have had DA. So this is just an example for you to see how it works. So as long as this condition is met, then while is running. Here, if this condition is happening, we are setting done to 1, which means done is true. That's when this loop will stop running. So this is going to continue until done is not true. Done is true. Let's go to MATLAB and practice these. So I'm going to open MATLAB. I'm going to create a new script today. So we just code in a script. Good. So we are on slide 13. That's true. Okay. So in your script, as I said, good practice is always start with clearing your workspace and closing all the figures and clearing your command window. So we want to have 2 variables. I'm just going to introduce these variables. One of them is x, which is 1 to 10. And one of them is y, which is a list of numbers. So I'm going to enter just random values between 1 and 100. You can just have as many of them as you want. I'm just going to do this 50, 85, 92, 75, 60, and 95. So this is my example y. So I'm going to show you a new type of graph or plot, and that's the bar plot. We are going to try to plot these against each other. So imagine we have 10 students, and these are the marks, the scores. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have 10 marks for them. So this is just to simply show you what a bar plot looks like. So in order to run this, I need to first save my script. So as you can see, it is called untitled and it has a star asterisk here. So if I save it, then that will disappear. I'm just going to put S3 for session 3. And you specify where it should be, and I will save it. Now I can run it. So as we discussed, you can simply press run here, or you just type S3 here without the name and press enter. So I will just press run, and it runs my code line by line, and this is the figure that it is going to generate. So bar plots are quite useful. You always need them. And this was just to show you that you can have bar plots. It's not just line plots that you can do or dot plots. You can do bar plots too. So I'm going to give it X label. So the X label was students from 1 to 10. And the Y label was their score or marks. And I'm going to give it a title. For example, first semester. Yeah. So if I run this again, it's going to close the image, open it again, run the lines, and this is now score and students, and this is the title, first semester. I don't have a legend because this is clear, it's just the marks. One way to save it is to save this picture is to just click on save as, and then a new window opens up. FIG fig is the default basically type for figures in order to save it. This is the MATLAB default. So if you save this as fig, MATLAB knows later on if you want to open it, it's going to be just a figure. But you have all these other types as well. So you have vectorized versions or just JPG, PNG, whatever you want. We have PDF. This is one way of doing it. So for example, you choose EPS, high quality, and you just press save and you save. If you want it to be done as a line of code, this is how you do it. So I'm going to do print minus DPSC, and I'm going to choose a name for the figure. Sorry, okay, graph. I choose the name. This is very useful to have it in your script when you want to export your images and save them as files and have them for future use. So I'm saving this as APS file, so it's high quality. If I run this, it's going to basically create a new file in my current folder, which is called scores.graph.eps, and this is basically this figure. So that was it. I just wanted you to know how to do bar plot and how to save your images as commands. So I'm going to close this and we move on. So this was the bar chart. Next, we do some if statements. So you can even just delete these or just create a new script. It doesn't matter. We don't need it anymore. So I'm going to load one of the built-in example data sets called serial. We have worked with this before. So it's called serial.mat. So I'm going to say we are loading serial data set. It is 3 o'clock, but if you don't mind, I carry on without a break, or do you guys need a break? Let me open Teams to see how we're doing. Okay. You can put your mic on and we just go for a break. Since we haven't done much coding, I thought we just continue. Well, I'm open if you want to break, we have break. Good, we keep going. So we have the serial data set imported. So if I run this so far, I can just press run. It is not saved, as you can see. This asterisk shows that it is not saved. It saves the file, and then we will see the data set. Always good practice, comment your code, because you don't know. It's not that you're going to give your code to anyone. You wouldn't remember what you have done a week ago. Always try to comment. I'm not going to do it all the time, obviously, because we don't have time for that. But try to do that. So I'm going to index into sugars. So we have a variable called sugars. I'm going to index to this. So it has like loads of numbers in it, 77 numbers for 77 different types of cereals. So I'm going to index to this and say if the second value of sugars is more than 5, then type this. So I want it to be like low sugar, for example. So this is a bit advanced. We have not had these before, but I'm doing it so you can see it. So we are going to, sprintf is going to type a message on the command window. And I'm saying type do not eat, which is just a string of words. So it's just going to type that. And if you use %s, then you can index into name, extract the second value of name, and use that string, put it instead of this %s, and that will complete your sentence. So if I run this, I will see that. So how did it happen? The second value in name was a string, so it was called 100% natural brand. So that's the second value. It's going to find this and replace %s with this string. So that's all it's going to do if this condition is met. So obviously the level of sugar in 100% natural brand was higher than 5. So I just didn't want to eat that. So I'm going to clear the command window. We keep the variables. I'm going to say now, if this was less than 5, we know that it is not, but I just want to use that as an example. Tell me the %s is fine. So that's fine to have because it is low sugar for me. That's going to again find that value in name to find that string, put it instead of %s. So I want to introduce other conditions. So I will say else if sugars, this time I'm just going to choose 13 randomly. If that was less than 5, so that's a condition for the value of sugars 13. So if that was less than 5, then type go for that one, %s, and name. This time it was 13. And if none of them was true, so for example, this wasn't low sugar and this wasn't low sugar either, then print just make an omelet. Yeah, let's. So if none of them was true, so they are not low sugar, I would just go for an omelet, and that's that. So if I run this now, what happens is that, okay, none of them was less than 5, so I should have an omelet. So this is now considering 2 conditions. So the first condition wasn't true, the second condition wasn't true either, and the third condition is the third statement is going to run, because if these 2 are not true, it's just going to go for else. Good. We move on. And you can have as many else ifs as you want. So for example, you can add one more here. So else if sugars 22, for example, was less than 5, then say go for copy and paste instead 22. So for example, I will run this again to see which one we get. Okay, great, 22 was fine. So 22 is this. It's just telling me that this one is lower sugar. Just go for that if you want. Good. Let's go for a different example. I will just clear my command window so I don't see this basically. So if I run this, oh, cancel. It's going to clear my command window, then I can continue. So let's have a new variable called fibrous, and I'm going to assign 0 to it. Let's have a for loop that starts from 1 to I starts from 1 to length of name. So this is, I'm doing it and then I will explain what's happening. So this is creating a for loop. The initial value is I, that's what is incrementing, that's how as many loops as we are going to have. So it's going to start from 1 to the length of name. You can choose this to see what the value is. The length of name is 77. You can see this here. So I'm saying start from 1 and repeat this for 77 loops. So it's going to do that. And I'm going to say change this value of fibrous, sorry, IM1, and put any value of fiber that is more than 4. And if fibrous IN1 is 1, sprintf the percentage s is good. I will explain what I'm trying to do in a second. Name I and end. So I'm now putting an if statement inside my for loop. So I'm saying go through all the values of fiber. Whatever that was more than 4, so I want to choose the ones that are quite fibrous. So I want anything that is more than 4. So in fiber, we have 77 values, and they start like from 0 to like, I don't know, the maximum. So 14 was the maximum. Yeah, 14 was the maximum. So I'm going to say, I just want those that are more than 4 to be chosen. And then if there is a value, so this equal 1 means that if this is true, if this exists, then print that that certain type of cereal is fibrous. It is good for me. So I'm going to run this now. So as you can see, it's just going to go through all these numbers from 1 to 77, and it's going to just type this statement if this condition is true. So if there was a value that had a fiber more than 4, so we are indexing into fiber, choosing the ones that are more than 4, assigning them to fibrous. If they are assigned and they exist, then it is going to print this. So I can see a list of all the cereals that have a value of fiber more than 4. So I think there are, how many of them? 8 of them. Yeah. So that's another example. This time I'm going to clear as well. So let's do something else. Let's start a new example. I have an initial value of 10. I'm going to do a while loop. So I'm going to say, so long as a is less than 20, f prints f, the value of a is percentage d. \n a, okay, and increment a by 1 in each loop. So what's going to happen? So initial value is 10. So if I clear everything, so command window is cleared, workspace is clear. A is 10. So I'm giving A an initial value. I'm saying as long as A is less than 20, so that's my condition, A is less than 20, then fprintf, what is the difference between fprintf and sprintf? Sprintf creates a string variable. fprintf writes to a file or to the command window. So they more or less do the same thing. I just want to see the output here. So as long as the value of A is less than 20, just type the value of A is whatever it is, and then go to the next line. This \n is new line. You might have seen this in other programming languages. So when you're just displaying a text, you can use that to go to the new line each time. So now I'm going to run this. And as you can see, it starts from the initial value. So the initial value was 10. Then it's going to say, okay, 10 is less than 20, print it. So it's going to say the value of A is 10. And then it's going to add one number to it, so 11. Then the next loop, it is 11. It's going to show that until we get to 20. So 20 is not going to be shown because I haven't set equal or less than 20. So it's not going to show the last value, which is 20. Good. Let's move to our slides. So what did we do? We used if, else, and else, and else if. We used while and ends, and we used for loops as examples. So this session, as I told you, is about programming. So one very important thing is that you keep your code readable to yourself and to other users. So if somebody else is looking at your code, it has to be nice looking and readable. So you have to first thing indent your code within the blocks. So between each pair of, for example, if and end, or if, else, end, or while and end, or for and end, it has to be indented nicely. So the statements normally go in, and then end comes in the same level as, for example, if. So you have to indent your code, and indenting makes it much easier to read your code and therefore easier to debug it. You know where the loop has started, where the if condition has started, and you can literally go through it and find the bug. And in order to do that, if you haven't indented, MATLAB does it automatically. So each time, for example, I was pressing enter, it was obviously indenting my code automatically, as you can see. So for if it did that, for loops, for while loops, it is doing it automatically. But even if I didn't have these indents, I'm going to just ruin it. If you just choose this section of your code, or just do Control A, or on Mac Command A, and then do Control I or Command I, it is going to automatically put them back where they should be. So it's going to do it for you automatically. So these are your new best friends, really. You need to always use them to make your code readable. Pre-allocating arrays is very important. So MATLAB keeps the arrays as contiguous blocks of memory. So if you are introducing a variable, it is going to assign the values inside the memory of your computer. And if inside the loop that variable is expanding, the size of it, then it's going to have issues allocating that variable inside those values inside the memory. So it's going to be sporadic, like it's one variable is going to be in 5 different places on your memory, and it's going to slow down your code. So if, for example, you know the size of a certain variable, I'm going to show you. So for example, here, the easiest way is to click on these orange things. So MATLAB is telling you that your code is not perfect if there is an orange thing. If it is red, this like a square is red, there's an error with your code. If it is green, you're good to go. And if it is orange, you should really work on your code. So if you can see, Fibrous initially was 0, but then in the loop, Fibrous was growing because I am assigning each output to one cell in Fibrous. So it's not good practice. You should not read it. If you can avoid that, you should avoid that. So if I knew how large Fibrous is going to be, it's better if you create a zeros vector or zeros matrix and assign that size to it. So when it is going on your memory, MATLAB knows how much memory it's going to take, and it's just going to have that memory allocated to this variable. And later on, it's not going to be problematic. It's not going to slow down or break or anything. So if you know how to pre-allocate, do it. Let's go back to MATLAB again. Any questions so far? Am I going too fast? No, we're good. I'm going to clear and CLC. Good. I'm going to remove these as well. So one example of pre-allocating is, for example, if I had n is equal to 1 to 50,000 or 5,000. Yeah, 5,000 is enough. X of n is n to the power of 2. So this is an example that we use several times. So for example, all I want to do is assign different numbers to n. So here, as you can see, MATLAB is telling me that if you can pre-allocate this, do it, because the size of x is expanding and is changing in every iteration. So if I want to pre-allocate this, how would I do that? So for example, I'm going to do this. I haven't run it, but it doesn't matter. I'm going to say, for example, the size of A is this. And I'm going to say, create a zeros of size A for X. So X is now pre-allocated. And then you literally can do the same thing and say, for example, in one column, just do this. So I know the final size of A is going to be, for example, this large. So why wouldn't I do this? So it is nice to pre-allocate X and then run your code. Second example for pre-allocating. I'm going to remove these back to slides. Good. So for good programming, always break your code. So if you can break it into small sections, do it. I will show you how in a bit. And in the scripts, you have seen it. So in the live scripts that we had for each session, I have broken each part that we go from the slides to MATLAB. I have broken it using 2 percentage signs. So if you can break your job, break it. If you can, for example, you have different tasks that are repeated several times, consider creating functions for them. So you just call those functions. You know now how to create functions. And if your task is really complex, excuse me, consider creating a flowchart of what you want to do, or Write a simple algorithm. Just tell yourself, okay, I need to initially do this, and then my code should do this. After a short period of time that you have done programming, this automatically happens in your head. You know, for example, in order to, I don't know, create a certain plot, what steps you need to go through. So you are coding in your head before you actually implement your code. Always comment your code. Please, please, please always comment your code. And as I mentioned earlier in the beginning of the session, use meaningful variable names. Keep them short and precise. If they have to be long, they have to be long. It doesn't matter. But it has to be meaningful so you know what they are referring to. Yeah, comment your code always. Then, yes, I mentioned that if you need to break your script into different functions that are repeated, for example, some parts of your code are constantly calling for a certain piece of script. So just take that, save it separately, always call that function or call that certain script in different parts of your code. And keep your code in one or more dedicated directories and have separate directories from your data. Don't keep your code in the same directory as your data. Always keep them separate. And for each project, have a separate directory and have separate sections, subfolders for each task. And for functions names, obviously you have to use meaningful names. And always include a help section at the top of your function, and that can include different information, including your inputs and outputs and any options that your function has. We will see this later as we move on. And I explained different subfolders for projects and applications. MATLAB only knows where your code is if where your command is, if that command is a part of the MATLAB core installation, or if it is in the same working directory, we talked about that, or if it is a directory that has been added by the user. We will do that in a bit. And this is very personal from me to you. Google, if you couldn't find certain things, always borrow, beg, and or steal code from your friends or colleagues. Don't waste your time, because whatever you want to do, probably someone else has done it before, unless it's something completely novel, and by that point you are good enough to do it. But if it has been done before, ask your colleagues. Don't be shy. Just get the code. People are willing to share, and get the code and just work on that. Don't try to program. Programming is just really changing what already exists, not writing new code. And as I've mentioned several times before, you cannot be taught to program. You don't learn how to program in this course. You're just going to learn by practicing and doing programming. And use the help system for MATLAB, from MATLAB, and obviously go to Stack Overflow, other websites to find answers to your questions about MATLAB. And if you're a bookworm, ask me what you want specifically, and I will try to send them to you. This includes like any topic in MATLAB that you want. I will try to find it and send it to you, an electronic version or something. Don't tell anyone. And practice. Please use MATLAB for anything and everything. And it will be slow and hard in the beginning, but obviously you will learn. So how are we doing? Do we still need a break, or shall I dive into image processing? We just are going to do some basic image processing if we do it. But if you want, we can have a 5-minute break if you just need to go to loo or grab a cup of tea or something. I'm going to see how things are. There are not so many of us today, so if you are willing to continue, I will continue. No? Okay, let's keep going. So the exciting part, it's not going to be long. I'm just going to show you some stuff. The exciting part of today's session is the image processing session, which I was really trying to get there quickly, but I hope it hasn't been too fast for you. So we have done some basic stuff, including importing an image and displaying it in MATLAB, and seeing like the size of the matrix of the image and this and that. But there is a lot more we can do, and this is the beginning of image processing. So next session is going to be more about image processing and segmentation and stuff. So image processing is basically referred to any technique that helps us modify images, use them, or extract like very meaningful and important information from them. As I mentioned, we already know how to import and display images. The first step obviously is importing the image into your MATLAB workspace. You know that already. And once it is in your workspace, you can use different MATLAB functions like display, like different functions that we have already used, imshow, to display, process, and to classify your images and do whatever you want to analyze them. So let's do some image processing basics. So I'm going to ask you to basically go to any folder on your computer that you have like at least 1 or 2 images, and they can be anything. So just go to any folder that you have literally 2 JPG or PNG or anything files. I will give you a minute to navigate to that folder. And we can create a new script in that folder. It doesn't matter. It's bad practice, but it doesn't matter. So just even copy 2 pictures to your current working folder, and we can work on those. So as you can see, I have these 2 images, 3 JPG and 8 JPG. As you can see, a brief, yes, like summary of them here. This is the image, these are the images, and you can see the size of them as well. So this is the width and height of the image. So there are just pictures of brains with tumors, as you can guess. So you can create a new script. So we start fresh, clear CLC, close all. I'm going to import the image called 3.jpg and save it or store it as a variable called I1. So how do we do that? You already know how to do that. So imread was the function that we use. Did I do it correctly? Yeah, that's fine. So I'm going to import I1. And as you can see, this is an image of this size. So it is 244, 207, and 3. So it is 3-dimensional. So we will talk about it. Let's show it, and I will tell you what that means. So let's see. First of all, let's see I1. Let's see what it even has. So as you can see, it's just numbers, like a lot of them. And because it is 3-dimensional, MATLAB is just showing them by the last dimension because they have 3 dimensions. So it is telling us the last dimension, it has these, the first dimension, it has this, these values, and then it goes to 2 and 3. It's a very large file. So let's try to just show that. So I'm going to create a figure. Yes. And then I'm going to show I1. So figure means it's going to open a new window. So if you run this, it's just going to open a blank figure window. This is it. There's nothing in it. And if I click on this or run that, then it's going to plot or show that image in figure 1 in the same window. So this is just showing it. Let's import the other image as well as I2. So I have another image called 8.jpg. And let's see that in a different figure. So imshow, I'm going to, did I close that? Let's just run that again to have the figure open. Good. This is figure 1, and this is importing figure 2, opening a new window called figure 2. It is going to be, and we're going to show that on top. So that's figure 2. So as you can see, this is figure, this is the file called 3.jpg. This is the file called 8.jpg. So if I want to show them together, I can use a function called imshow pair and have I1, I2 in the format of a montage email. So this is going to be a new window, and it is just putting these two next to each other. So it is not a subplot, but it is similar for images. And it's just going to put the figures next to each other in the same order that you have specified. So it is a very useful function. Let's do some basic image processing on these two figures. So because your figures potentially are different from the figures that I have. Of course, these two are already in that Google Drive folder if you want to work on these. But I prefer to work on something we all can work on. So I'm going to use the peppers image again. So I'm going to close these and just go to my script and just import the peppers image. So it was called peppers.png. into my workspace as I. So I'm going to clear my workspace and my command window and input peppers there. Good. If we show it, you saw it before, it's going to look like this. So it's just a picture of bell peppers and different types of peppers and garlic and onion. Then as we discussed, I is a large variable. Yeah, it's very large. So the size of it, let's see the size of it. Of course, you can see it there in your command, in your workspace as well. But if I enter that, we can see the size is 384 by 512 by 3. So does anyone know what that last value? We know that this is like the number of rows, the height and the width. Does anyone know what this 3 is? Any random guess is accepted. Oh, we have a comment if I can find it. 3 colors, 3 color guns. Good, RGB. That's it. That's it. Wonderful. Good. So images that have colors are basically made from three main base colors. So they are red, green, and blue. And so these values, those three dimensions, refer to how much red, green, and blue that image has. So we can basically, if I can minimize this, yeah, we can basically see what the third dimension, how much green do we have? So let's assign that, assign that to a new variable called G. G stands for green, so it is literally in the same order R, GB. So G is the second dimension. So let's see G. So I'm going to create G, and let's have a new figure and show G. So let's see how G looks like. So this is how it compares to the first image. So as you can see, another thing to notice is that this is called, this is of type uint8, which means there are 2 to the power of 8 numbers in it. And those numbers, as you all do image processing, refer to the intensity of, if it is black and white, so intensity of, for example, black and white, or intensity of these RGB colors. So here we are looking at the intensity of green, and 0 is dark. And as we go to 2 to the power of 8, which is 256 minus 1 is 255. 255 is the maximum. And 255 is the highest amount of green that this image has. So as you can see, these light parts, they have a lot of green in them. But you can have a look at like red and blue as well and see what you get. I'm going to leave that to you and move on. So another way of separating them is to use the function. So you can do that individually as we did it like here, just index into R, or you can use the function imSplit. So it's going to split the image I into, 3 different outputs of red, green, and blue. So let's run this. And if I now show, for example, let's do a montage of the image itself, the red part of it, the green part of it, and the blue part of it, and create that in a new figure. Let's see what we get. So this is now a plot of everything that I did in this order. So the first image is is the original image. This is the red one, this is the green one, and this is the blue one. So if you compare them against each other, then you can see how much of each color is hiding in this picture, basically. So that's another very useful set of like built-in commands that you can use, built-in functions that you can use. Another one is grayscale. So most of the time, we want to change our images into grayscale images. Why? I will explain that. So imShow. So there is a function called im to gray, image to gray. So it's going to change my color image to a grayscale image. And it's going to store that in a variable called GS. And if I show GS, it is going to look like this. So this is a grayscale version of the image, the colorful image that we had. So what is the size of it? As you can see, GS is now 384 by 512. all of these separate colors were of the same size as well, which is just the height and width of the original image. It doesn't have those 3 dimensions anymore. Changing into grayscale, it simplifies our life because it is easier to work with grayscale images. It has lower dimensions. It is smaller to save it on memory. It's just a lot easier to work with grayscale. So it is preferred sometimes when you are doing image processing to just work with grayscale images. Another function is looking at a histogram of the figure. So the original figure was called I. ImHist shows us a histogram of the intensity of colors, everything about the image in this histogram. So now, if I look at I will keep this here. And let's look at a new figure, the histogram of the grayscale one. In a new figure. So if you have a look at these two, they look quite different. But basically, you can still use the grayscale and get so much information out of it, and it is normally enough. There is a way of adjusting the intensity of the grayscale images, and I'm going to just create a new variable called GSAdjust because I want to adjust the grayscale image and store it in that. And then I will show you the histogram of that adjusted one. What did I call it? GSAdjust. So this is again another built-in function that is just going to adjust the intensity of your image automatically. You can do it manually. I will show you how in a bit, or you can do it just automatically using ImAdjust. So this is the adjusted histogram. It is, as you can see, choosing cropping this one from here more or less up to more or less here-ish. So it is just going to take out the intensity that you might want to work with. So that's another one. And if you have this is adjusting automatically for grayscale, so you use ImAdjust. If you want to adjust the colored image, so the colorful one, so it is a different function called image local brighten, and that's how you adjust the I'm going to put these together, the colored one, to just have a look at the the adjusted version versus the original version. So potentially going to be, figure 2, the last figure. So this is now adjusted intensity. It's like filtering it. Basically, you're just removing unwanted intensity lines in your figure. So this is the original image, and this is the adjusted automatically one. So all of these that we talked about, you can code them, or you can go to your, if you are in MATLAB desktop, or I think in the online platform, it is there as well. You can go to your apps and choose Image Viewer. So this is a very helpful tool. It opens in a new window, as you can see, or I can type imtool in my command window. And again, it opens a new window for doing all of these. So I can open a picture, I can import it from my workspace. So if I want to open it, I will just press open and choose any of these images. So I have another picture of breast cancer here. So this is an image of a cancerous breast. So you can do different things here. So here you have eye. If you click on it, you see basic information about this image. So the size of it, what class it has, the intensity, maximum and minimum. So it starts from 0 to 242. So we know that the maximum, because it is uint 8, it's 8-bit, so it's 2 to the power of 8. The maximum intensity is 255. But for this image, the maximum intensity is 242. And you can see like where it is located, when it was modified, different types of information about this image. Then you can use this option to basically go around the image. So this is showing us each like combination of the pixels in this square, and you can move it around and see different parts, or just minimize it and move it around, hopefully, yes. And it shows you different numbers of intensity. My computer is a bit slow, yours might be a bit fast. So it shows you different intensity. I mean, this is quite large, yeah. Intensity values of each of those pixels. So the size, the height and width specify how many pixels we have in the height and width of that image. And as you move, you can see the intensity values. So if I go, for example, to the dark section, the intensity is basically 0, obviously, because it is dark. And if you go to the brighter sections, you see that the intensity changes. Another thing you can do is adjusting the contrast. So that's the thing that we were doing automatically using the commands imadjust and imLocalBrighten for colorful images. So you can basically adjust the contrast of the image. So I can just say, as you can see already, the image is changing. I can just say I want to see just certain things on the image. And as you move, you can already see the very bright cancerous parts of the breast. And you can literally change this to whatever you want. So this is the histogram that you are changing. So you are focusing on different intensity levels in the image. And after you did that, you can, or you can just eliminate the outliers, anything that you want to do with the image, really. And you can adjust the data and even save it. I mean, I can now export this image to my workspace and then use that adjusted image. Good. Let's go back. So we did the basic image processing. I'm going to wrap up. We have 8 minutes. So the first value returned by size is the number of rows. We know that, and it corresponds to the height of the image. The second value is the number of columns in the array, the pixels in the columns, and it corresponds to the width of the image. The third number or dimension is because the imported image is a color image, and so it needs a third dimension to store the red, green, and blue color planes. We can index into these planes, which we did. Why do we convert to grayscale? So grayscale is going to occupy a third of the space required by an RGB image, a colorful image. We talked about it. So it requires less computational power to process and can reduce computation time, obviously. And developing an image processing algorithm can be more straightforward when working with grayscale because it's easier. We talked about the image intensity. So when you are on the dark pixels, they might be between 0 to 100, and not many bright pixels have intensity values above 200 because it gets very, very bright. But you know that if it is an 8-bit image, it's from 0 to 255, which is 256 values, 2 to the power of 8, always remember. So you can increase the image contrast brightness to see the brighter pixels, and you can change it to see the darker pixels with im adjust. And if you have a colorful image, you can use im local brighten. You learned now how to basically use the image processing, basic image processing tools of MATLAB to display an image, inspect the size of the image, and see the intensity, the colors, the grayscale values. You can adjust for brightness on grayscale images automatically or on local images, colorful images. And you can basically export the final image accordingly if you want to use it in your workspace or just save it. That's all I have to say for today. You can now finish MATLAB on-ramp, obviously, and you can complete the first 2 sections of image processing on-ramp. So as your homework, please complete the final project of MATLAB on-ramp. We're going to go through that next session. And there are no exercises on image processing per se, but please go ahead with image processing on ramp. It is very useful, but you will see exactly what you learned today. It's just for more practicing. Thank you very much for being with us today, with me. And I will see you in 2 weeks' time. The next session is 22nd of March. Any questions, please let me know or drop me an email. And take care and have fun. Until then, I will stop the recording and I will, as usual, share everything on our Google Drive folder. Thank you very much, everyone.